Thank you for being here. Good afternoon, everyone. Like you know, getting your model to work in your notebook is one thing, but actually running it in production and making it available to your end user is a different ballgame. It's more complex and expensive. Many teams end up compromising between speed, scale, or even their budget. Over the next couple of minutes we spend together, I will walk you through the GKE 4-layer playbook that shows you what teams like Google's own Vertex AI has done, and teams like Snap and TII have done on GKE. I am Fisayo, a product manager for inference on GKE, and with me is Akshay, who will be presenting also. He leads product for AI inference on GKE. We were supposed to have Mouadh with us today from the Technology Innovation Institute in Abu Dhabi, the team behind the Falcon open source model. He couldn't make it here today. However, Akshay will cover what TII was supposed to present, so he will show you how TII runs this Falcon model in production on GKE today. This is a story worth waiting for. You don't want to miss it. So here's what we're going to cover during our time together. I'll frame the challenges faced when serving AI inference at scale. Then I'll go through how GKE approaches this. After which, I'll provide a deep dive onto GKE Inference Gateway playbook. I will also take you through the first couple of layers here. I'll take you through routing layer here. I'll take you through serving layer. Then Akshay will take you to how you can source capacity effectively and maximize your storage. At the end of the day, we'll share production numbers, so you know this is not just theoretical. This is actually what works today in production. And we'll close by answering any questions you might have for us. So, balancing latency, throughput, and cost remains one of the hardest operational problems you face in Gen AI today. I'm sure this is a commonplace for most of us. This is not news. And let me show you why that happens. We always have these three forces fighting against each other. You need to prioritize latency. Your users expect sub-second response time. Then throughput. You want to maximize the accelerators you're paid for, and you want to handle every request that comes to you. Then, of course, there's a budget part here. You have a fixed budget you want to spend to serve this model, and the cost you spend on serving this model needs to make sense to your business. And the reasons is something we've all seen. You have your GPUs lying unutilized, then all of a sudden there's a spike. You try to spin up the next pod. It takes a couple of minutes before it starts. By that time, you have a long queue of requests waiting for you. Your users experience, undesired experience on your application here. Then you want to switch between hardwares, but you're tied to that proprietary hardware you've been using, and you find it very difficult to switch. This is what we're going to cover in this session. Our goal is to provide a playbook to fix all of this, layered by layer. Google Cloud provides a full-stack approach to deliver frontier inference performance. Here's a blueprint of what this looks like. We have a 4 integrated layer approach here. Layer 1 is routing. With the routing, we have Inference Gateway powered by LLMD as the brain to help you determine how to optimally route traffic. So it determines the best pods you can route your traffic to, leveraging real-time information from your GPUs and your memory state. Then layer 2 is what we call the serving layer here. GKE orchestrates any model server you bring here. So if you're running on vLLM, you're running on SG Lane, or TensorRT, or even your custom model here, you pick the model server that works for you, you pick the hardware that works for you, and let GKE help you with your orchestration here. Then we have layer 4. All of this, you need the capacity to run this traffic we've been talking about here. So in layer 4, we're going to look at how do you source capacity effectively, getting the best price that makes sense for your particular use case. Then we end with layer 4 here, which focus on storage here. So we have the rapid cache, which is also known as anywhere cache. Some of you might be familiar with that name. It helps you kill that cold start when you're trying to start up the pod here. And we also have managed cluster here. it helps you maximize the caching you have. So imagine you already have this context here. Instead of reprocessing it here, it helps your pod share this context it has here, making you prevent that rework computation cost. And each of these pieces I've mentioned here are open and modular. You can decide to adopt a full stack approach, or you might just pick that particular layer or component that addresses your particular friction or pain point. So I will pause here, and we want to take a look at this. We recently just relaunched LLMD Prism. It's our open source tool for inference performance analysis. So to validate the benefits of these optimizations I've mentioned, we did some analysis to understand what is the performance difference from if you use as is, like the status quo Kubernetes deployment, versus if you use this optimization. And as you can see, in this orange line I have here is when you do nothing. It's like this inference workload with the standard deployment. And for the blue line I have here is the kind of performance gain you can achieve if you go ahead and make use of this improvement. In this chart here, we leverage Inference Gateway with prefix-aware routing here. And as you can see, the results speaks for themselves. We achieve up to 147% increase in throughput and 98% reduction in latency. So you can stick to the status code, but you might be missing out on possible production gains that your workload might benefit from. So this is not just theory, this is like production results. So this is the result from GKE Inference Gateway being used on Google's own Vertex AI. And you can see here, first, we're able to reduce time to first token by 35%. So essentially, we slashed the wait time for that first token by a third. Then second, we double the cache hit rate. What does this mean? It means that it makes conversational workload significantly cheaper. So we're able to reuse the same context and don't have to process it over and over again once we process it once. And finally, we achieve 2x better P95, ensuring your tail latency stays stable even when the traffic doesn't. So this is an example of the dashboard for Vertex. And this shows you the before and after. So you can see that before Inference Gateway, you can see how the traffic was. And you can see after Inference Gateway. So you can see that cache hit rate doubles, just as I just mentioned now. So we have seen some of the impacts. Now let's dive into this playbook. We're going to walk through each of these layers, starting from intelligent routing. And here is where the biggest day one win comes from. So let's take a step back here. When we think about it, standard load balancers, they fly blind, and they treat every request the same way, like you can see in the image I have here. When the next request comes, it doesn't look at the particular state of your pods here. So a small chatbot request that says just hi can get stuck in a big data job. And this makes your application slow and unreliable. And secondly, standard load balancers here, they spike your bill because they have no idea of what the GPU holds in memory. So when a new request comes, it's always forced to start from zero for each time. So even if it has the content for your new prompt, it's going to process it all again. So you are just piling up a huge rework cost here that you don't need to pay for. So with GKE Inference Gateway here, we have 4 key functionalities, and let's go into them. First, we have your load-aware routing. So thinking about the problems I just mentioned now, so the load-aware routing scrapes real-time information of your GPU or TPU metrics. Things like the length of requests on the queue, the memory state, your KB cache utilization, you name it. We extract all of those details in real time here. Then GKE Inference Gateway also has this content-aware functionality here, where it knows which pod has a memory you need here. So if a request comes that you already processed it, it's going to send it to that pod that already has that content. So that's why we're able to achieve that higher hit rate that I mentioned earlier. Then we also have the admission control within Inference Gateway here. So this acts as your bouncer here. It protects response time by managing traffic during heavy spike. Then we have the predictive latency aware scheduling. This is new. So like the result I showed you before, we didn't cover that. But this is new, we just launched this recently. And this predictive latency aware routing takes it a step further. So not just providing information based on the information we have now, but it actually forecasts what the performance would be. And I'm going to take you a step deeper into what it actually does now. So like we all know firsthand that manual tuning is like a lost game. Imagine you finish fine-tuning your workload today by noon, and by 5 p.m., it all goes wrong because things change. And we need a way to adapt to the changes in our workload here. And to solve this, we have trained an adaptive machine learning model here that takes this three-step approach. First, it observes your gateway at real time. It collects the real-time telemetry, everything from the queue depth to the current cache utilization. Then next, it predicts. So this lightweight AI model we've trained here collects traffic details, live traffic details. Then it can forecast how fast each pod will respond. And it currently has hit up to 95% accuracy. And what does this do? Instead of just picking the fastest, it picks the best fit server. What does that mean? It ensures you meet your latency target while keeping your coldest port free for future spikes. So let me show you what this looks like. If you look at this chart I have here, this shows you a comparison of workload that use manual tuning and workload that has used this predictive latency aware scheduling I just mentioned now. If you look at the green line, whether you're looking at the P95, time to first token on the left, or you're looking at the throughput on the right, with the predictive-based model, you can see that the traffic stays constant. It's actually predictable. It effectively avoids the queuing delays that will usually kill your tail latency, even as you hit saturation. And if you look at the orange and red lines here, you will see that even when it fails, the green line stays flat and is very deterministic. So you can actually predict the performance of your workload. So you can actually inform your decision making. So this shows you that the difference between when you follow a script and when you let your system actually think. So next, we're going to look at how you serve. So we've looked at how you can route intelligently now. Now let's look at the engine room where those models actually live. We are all conversant with this, that scaling inference is often a choice of, you have this hardware silo, you probably have used this particular GPU spec, and you need capacity for the next time, and the particular capacity you use is not suitable or available for your scale. And to do this, you probably need to fix your code so you don't have that flexibility to move quickly. Secondly, we are tied to closed ecosystem where you stick to one vendor, but there's this new improvement, and you're waiting like 6 months for those new improvements to come to pass on your own particular orchestration stack. So our playbook breaks this silo by prioritizing future-proof. One of the things we do is this. GKE is open and is runtime agnostic. So regardless of your runtime, like I mentioned, you bring it and we can orchestrate your workload for you. So one of the things we do is this. If you use vLLM, SGLane, Dynamo, Tensor RT, or your own stack here, you only need to provide the metrics we need and we can actually orchestrate your workload. And we're investing heavily in the open source community here. So we're leveraging the architecture from LLMD here to provide well-tested reflex architecture that actually work and give production results. So you have to avoid the guesswork. I don't need to go through the churn or benchmarking afresh because we give you real production results here. And also, you have the freedom to choose what works for you. You can choose the best performance price for your workload. So you can switch from one hardware to another and still gaining the same performance gains without rewriting your whole stack. So this is not just theory or philosophy. It's something we're actually doing in reality here. So Google is one of the builders of LLMD, which is an open source framework that provides what we call well-lit paths. When I say well-lit paths, I mean tested reference architecture built specifically to solve the biggest blockers of latency and cost. So whether you're optimizing for operational simplicity or you want to be able to mix hardware, LLMD is that easy button for moving from notebook into production with operational confidence. So this is something we have done. And this is not just from a Google perspective. We've seen customers actually use this and seen the same results. So this is a production validation from Snap. They've used LLMD and they were able to hit up to 80% cache rate improvement. And they were able to integrate it seamlessly into the existing Envoy service mesh. So this is very important. So this is us meeting them where they're at. They didn't have to rewrite their whole stack to actually plug this in. They're able to leverage the part or component that makes sense to their specific workload, and they're able to gain the same kind of result we're seeing here. So we've gone through those details here. And now, if you don't have the capacity to run this effectively, this will be a waste. So Akshay will take you through how to source capacity effectively and getting the best performance costs.
Thank you, Fisayo. As Fisayo said, we walked through the routing and the serving layer. We're going to walk through sourcing capacity. As you may all know, you must have read in the news as well, there's a capacity problem in terms of sourcing accelerators. So what we see customers do is one strategy. One strategy is just buy as many accelerators you can. And that's a fair strategy. Effectively, if you know you're going to grow into all the accelerators you require, that's a good strategy to have. But what we also see is Google Cloud offers many alternative capacity procurement options. There's Spot. There's dynamic workload scheduler where you can effectively get capacity for a certain period of time. And what we heard from customers is, hey, you have all these amazing models, procurement options. How can I easily give you a sense of priorities of what different capacity types I want, and you do the scheduling for me, such that I can actually make use of these additional capacity options we have for customers. So that's where custom compute classes come in. Custom compute classes have been around in GKE for a while. The genesis of this feature was more around traditional applications where you could mix on-demand and Spot and reservations. But what we're realizing and hearing from customers is a great fit for accelerator-based options as well, especially for inference. For example, here, what custom compute classes allow you to do is to specify a priority of procurement options. You can specify your reservations. If you already bought your reservations, you can use them, obviously. And then if you want to burst out, you can say, hey, if I have my batch inference job, I'm also willing to utilize something like Flex Start, where you get a cost benefit, obviously, for using a more flexible option than just reservation. And you can obviously get it on demand as well, so you don't have to lock in your commitments. And then you can also use Spot VMs. What we're seeing is customers' batch inference is a great place to use Spot inference. Spot VMs are great for batch inference because they're usually interruptible. So custom compute classes is something which you should definitely consider because it gives you the priority on how you want to schedule across different capacity provisioning models in Google. So we took a look at the sourcing capacity options with custom compute classes and how you can actually specify your priorities. Let's take a look at the last piece of this playbook, which is the actual data and the storage part of it. So there's actually two big problems here with data and storage. The first one is when you're actually downloading the model weights, usually from Google Cloud Storage, those weights can be multiple gigabytes, tens of gigabytes. And it obviously takes minutes for these weights to be downloaded from Google Cloud Storage. So it obviously impacts your costs and your scalability because you're waiting for the weights to download, and that's time you're not serving customers' workloads. The second problem is around KV caching. As Fisayo showed, in the routing layer, there are many different techniques and algorithms we've built into the load balancer to route based on where your cache is already computed. But there are techniques also at the storage layer where you can actually expand the capacity of the cache and decouple the cache from the lifecycle of your pod. So effectively, even if a pod goes down, you still have the cache, and you kind of decouple that lifecycle so you can improve your hit rates and your latencies as well. The first problem we solved with something called rapid cache, which was formerly called anywhere cache. And the approach here is you get up to 4.8x speed up in your download. So effectively, your model load time goes down to tens of seconds, order of magnitude, for a pretty large model. And how it works behind the scenes is there's two options. There's two knobs. One is on the server side. Server side, you enable something called rapid cache. And GCS, it's a feature of Google Cloud Storage. And you get up to 2.5 terabytes per second automatically provisioned behind the scenes using local SSDs, but that's all behind the scenes. So you effectively just enable the feature. And the nice part of the feature, it follows your compute capacity automatically. Wherever your GPUs are, the cache is enabled server-side for you. We also have a client-side acceleration through something called Run AI Model Streamer, which we worked with NVIDIA. So both of them work well together. And they're super simple to use. You effectively just enable the cache on your bucket, and you enable parallel downloads on the pod, and they work together to really speed up the download time of the model weights. The second problem I laid out was about KV cache and how do you expand the capacity of the KV cache. As Fisayo laid out, we're really working with the open source community with LLMD. Shout out to the LM Cache community. That's another community in the open source inference ecosystem that we integrated with. And we integrated a third layer of storage with our managed Lustre product. So effectively, your cache flows from your HBM, which is on your GPUs or your TPUs. It then goes to the CPU RAM. And then finally, it uses Lustre also in the back end, and the benefit of Lustre is it's decoupled from your compute. So you effectively share it across all your GPUs. And even if your pod dies, because it's decoupled from the accelerator itself, you can survive any scaling event or a disruption event. And of course, it's really, really high capacity and petabyte scale, so it's very scalable. And based on our benchmarks, we benchmarked it for long context workloads. Long context workloads obviously benefit from a larger cache because your cache, your KV values obviously go up. And that's, we saw a 75% throughput gain, obviously a 40% time to first token, and you can use fewer GPUs as well because you're caching a lot, you're hitting a lot more caches. So that's another optimization we have at the storage layer. So as Fisayo laid out, we have a four-step assembly line. Each step has optimizations you need to think of. They're composable. You can pick and choose. You can use all of them together to benefit from the compounding effect. So let's take a look at what TII has done in production to actually benefit from some of the features we laid out today. So Technology Innovation Institute, based in Abu Dhabi, has three layers of models. They're a foundational model builder. All of these models are open source. It ranges from extremely state-of-the-art multi-model with Falcon 3. That's the latest model which is available. A kind of balanced model in the middle with the hybrid Falcon H series. And of course, smaller models for lower cost and higher throughput scenarios where you don't want to consume too much memory. So it's like a full spectrum of models. When TII came to us on their inferencing needs, this is something we see from a lot of AI native customers is there's the research lab. The research lab wants to move fast. They want access to GPUs. And they use different frameworks as well. Specifically with TII, they were using Ray for the training and their post-training. And then there's the whole production stack, which is the usual where you have to apply the best DevOps principles of reliability and scalability and make sure the capacity is available, can scale well. So there was two separate stacks, unfortunately, which were kind of siloed. And when they came to us, and this is the quote which was the result of it, and I'll walk into it in detail next, is before working with us, there were two separate stacks, as I said. They were operating Ray serve to also serve production because Ray was what the research team used. But this is where the infra team came in and worked with us and say, hey, Kubernetes has been around for a long time. It's the serving stack which has been around and has been used in production by many, many customers. How can we also combine and consolidate both the research stack and the production infrastructure stack using the same underlying compute platform? In this case, it happens to be Kubernetes and GKE. And moving to and using components like Inference Gateway obviously help them benefit from a lot in terms of latency and throughput. But also Kubernetes itself gave them benefits of faster GitOps and all of the other best practices you get, or the benefits, I should say, you get from Kubernetes, as you'll see later as well. So this was basically their architecture. They're like, hey, the research sandbox uses Ray. We support Ray on GKE. So they can effectively do their training and their post-training runs on GKE. And of course, the production serving engine as well. So that's also hosted on GKE. And they use Inference Gateway to route across their accelerator clusters, which happen to be across clusters and regions as well, which GKE Inference Gateway supports. So what does that mean for them, and how do they benefit? At the high level, it's obviously like you have economies of scale because you're using the same compute platform for both research and production inference. You can share your capacity. It's obviously a lot more lean in terms of operations. You don't have two different stacks. And of course, the production grade, like using the best practices, Kubernetes and GKE deployment gave them like a really, really highly available infrastructure stack. So these were some of the metrics they shared with us. They were monitoring different stacks. Obviously, when you have too many different teams using different stacks, you're monitoring many, many more components. So they could, by consolidating it on GKE, they could move from 4 components monitored to 2, which obviously saved them a lot of different moving parts. This is super important because they want to move really fast. The goal of infrastructure is just to support the research. And the research is moving really, really fast. Because they were able to consolidate it, there were no silos. They were able to go very, very quickly. And the research org is able to self-serve infrastructure very, very quickly and even serve production models as well using standard Kubernetes deployments and templates. And of course, GitOps is like, it has been the benefit of Kubernetes by many, many, many customers. And of course, TII being a research lab, they went from being a super research lab to like, now actually a production scale deployment with their Falcon app, and they're using the best practices with GitOps as well. And of course, not only did they use things like vLLM and Inference Gateway and all of the best practices we laid out earlier, they also used Anywhere Cache, which is now called Rapid Cache, to also like benefit from the cold start latency. So they benefited from Inference Gateway, from using vLLM, all our open source investments, as well as our storage investments here with Anywhere Cache. So that's it. We really look forward to like learning from you. We have all our reference architectures here in LLMD. It's an open source community. As you know, inference is a fast moving space. The conversation is always ongoing. So we look forward to learning from you, learning about your use case. And please contribute to the community as well. It's a very vibrant community. And also the predictive latency-based scheduling, which Fisayo introduced, we've also linked it there. Also available via LLMD. So all of this is available via open source, and we look forward to working with you. Fisayo and I will stand here for questions. We're happy to answer any questions you may have. Thanks.